On this week's cover, you can see the Mars Curiosity rover taking a selfie, a photograph of the machine taken by one of its own 17 cameras. After a year on the surface of Mars, the most technically advanced geochemistry lab ever landed on another planet can sometimes act just like a teenager on Facebook. Of course, researchers have also been receiving massive amounts of more useful data. This week, Science publishes 5 reports on the mission's initial results. Lori Leshin is here to fill us in on the analysis of soils, rocks, and atmosphere from the red planet.
Well, this week in Science, we are publishing the first solid sample analysis with Curiosity, where we took a scoop of fascinating Mars dirt and fed it into our high-tech analytical laboratory. In my paper, we specifically heat up the dirt and look at the gases that are evolved when we do that. And we find lots of water and other interesting stuff.
All right. Well, can you describe the setting for us? Where is the Mars rover, and what are some of the features it's currently investigating?
So Curiosity is in the floor of a wonderful crater called Gale, and we are currently doing our very best to race across the floor of this crater to get to the mountain, Mount Sharp, that we came to really visit and study in detail, to drive up it and look at its layers and things. For our paper, we actually did this work within about the first 100 days of the mission last fall after we landed, where we found a nice drift of sand and scooped it to be our first sample.
And that drift of sand is called Rock Nest?
It is. It's called Rock Nest. It was a beautiful area sort of behind a little pile of rocks, if you will, and it looked like a little rock nest, so that's why we called it that.
Okay, so you looked specifically at volatiles and isotopes from the sample at Rock Nest. What did you find in your analysis of those?
So let me explain the experiment just a little bit, because it's really fascinating. So what we do is we scoop up the dirt and we sieve it a little bit, and then we deliver it in tiny little portions. So it's a portion about the size of half a baby aspirin. So it's really not very much stuff at all. And we dump it into a little oven. We heat that oven up to about 1,500 degrees Fahrenheit, or 3 times hotter than your oven at home. So we're really cooking the stuff really nicely. And we monitor the gases that come off all the way along. So we can see things like water is released from this sample, around between 2 and 300 degrees. We can see carbon dioxide coming off. We can see oxygen released. And then we try to correlate those gases to different minerals breaking down inside the dirt.
Okay, so what were you able to find as you heated up this material?
So we found a lot of water. To me, that was one of the most fascinating findings. About 2% by weight of the dirt is water. And so to me, that's interesting because it's a good resource for potential human explorers. We know that one of the reasons the dirt on Mars is so interesting is that we think it's probably pretty much the same everywhere you go. So by studying it here in Gale Crater, which is really neat, we learn about all of Mars. So 2% water means that if you had, say, a square foot of this, or a cubic foot, of this soil, and heated it up, you could get about 2 pints of water out of it, or like 2 bottles of water like you take to the gym. Worth of water in every cubic foot of soil. So it's pretty good stuff.
And it's not just, you can't just squeeze it and get water out. You actually have to heat it. It's bound up with things.
That's right. You have to heat it to a few hundred degrees, so not too hot. You don't have to heat it to 3 times your oven. It actually came out at relatively lower temperatures. But you do have to heat it a little bit to get that water out.
And how does that compare with, say, a cubic foot of dirt on Earth?
Yeah, that's a good question. So there's a lot more water in dirt on Earth, maybe 10 times as much. Okay. So it's not as much by far as Earth. Of course, we wouldn't expect that. There's water everywhere on Earth, right? And Mars we tend to think of as a pretty dry place. So the fact that this water is trapped there right at the surface is pretty interesting.
Mm-hmm. And so what about the other kinds of volatiles that came out of the dirt?
So the water is kind of the good news for the future explorers. On the flip side of that, that's the classic double-edged sword, right? There's some bad news for human explorers. So we found the oxygen that was released with chlorine gas as well, and we think that was locked up in a mineral called a perchlorate. Those are, toxic. It makes your thyroid not work right if you ingest it. So it's something to really watch for. It's only about 0.5% of the soil, so it's not very abundant, but it does seem to be there, and it's probably in other places on Mars as well. So it's good to know now that it's there so we can plan for when humans go to Mars and there's dust everywhere. How are we going to deal with that issue?
Oh, really interesting. And what about the presence of organic molecules? That's something that everyone's really been interested in.
Absolutely. So clearly one of Curiosity's key missions is to understand the potential for Mars habitability, and key to possible life is the building blocks of life are organic molecules. And so we have a very sensitive sniffer on Curiosity to look for organic molecules. That's our instrument SAM that we used to make these measurements. And we did detect a few very simple organic molecules, but we think that they are actually reactions that took place in the instrument between some of the chlorine that was released from that perchlorate and organics from Earth that are in the background of our instrument. So we can't prove that those organics are Martian, and we, in fact, think they probably aren't. So this might sound not as good as we'd like, but the truth is that we really didn't expect to find organics in the dirt. It's a pretty harsh environment right at the surface of Mars with a lot of radiation, and it's pretty oxidizing. So when you're looking for organics on Mars, preservation is the key. You've got to find an environment where they won't be lost and broken down over time. And the dirt's not a good place for that on Mars. That's why we brought a drill with us, so that we can drill into rocks where things might be better, should be better protected from this kind of breakdown. So that's something that we'll be doing in the future, is actually looking inside of rocks for organics.
Okay. Well, you made this point earlier about how there's some homogeneity across the surface of Mars, that looking at RockNest will give you insight into the rest of the planet. And in the paper, you also talk about how sample analysis like this tells you about mixing of materials from the interior, the surface, and the atmosphere. What did you learn here about those processes?
Yeah, absolutely. So one of the things we're trying to understand is the sort of cycling of volatiles on Mars. So we think about the water cycle on the Earth. Well, what's the water cycle on Mars? And we'd like to understand how the different places, like the atmosphere and the interior and the surface, interact. So the tool that we use to explore that are isotopes, so looking at regular hydrogen and heavier hydrogen called deuterium, and the relative amounts of those two in water. That we know the atmosphere has a very special composition when it comes to deuterium. It's very deuterium enriched because hydrogen is lost from the atmosphere over time and the deuterium stays behind. So the atmosphere gets very deuterium rich. We see that same deuterium enrichment in the water that comes off when we heat up the RockNest sample. So that tells us that the dirt is, in fact, sort of like a sponge for the atmosphere. It's soaking up its water by interaction with the atmosphere. So that's telling us that there is probably a larger reservoir of water we need to consider, not just what's in the atmosphere, but also what's in the near-surface crust as that kind of superficial reservoir on Mars.
Okay. Your finding is part of a package of reports this week that we're publishing in Science. How do those reports and your reports all fit together?
Yeah, it's been a great thing to get to work on this group of papers together, and it shows, I think, the power of Curiosity's diverse but integrated payload. We have 10 different sensors with us up there on the surface of Mars. It's the most advanced mobile laboratory ever sent to another world, and so we get to use these results to sort of play off each other. So one great example is the companion papers talk about mineralogical analysis of the RockNest dirt, and they show a mixture of minerals that look like they came from just grinding up physical breakdown of volcanic rocks, and then about maybe a third to a half of the dirt is stuff that doesn't have a good crystalline structure. It's amorphous. It's very interesting. What they didn't see is minerals that have water in them that would be released at the temperatures where we see all this water coming off. So that's pretty interesting. So what that tells us is that the water itself is probably trapped in this stuff that doesn't have a good crystalline structure. It's in that amorphous phase. And that can teach us something about how that amorphous phase formed, probably, again, in contact with the atmosphere, been exposed to that radiation near the surface, and it lost its crystalline structure.
What's next for this mission? You said before that it's heading for Mount Sharp. Are there going to be measurements along the way?
There are measurements along the way. In fact, on our way to Mount Sharp, we have 5 different waypoints picked out for places that we can stop and do some more detailed analysis. We are trying to make tracks, though, so we're sort of drive every day we can drive, and we've picked these few spots to stop. We just stopped at the first one. I think there was a press release out in the last few days that talked a little bit about our analyses at Waypoint 1, as we call it. And we're driving like crazy, hoping to get to the mountain as soon as possible. What we can see there are gorgeous layers making up Mount Sharp, and those layers will tell us a story about how the environments on Mars have changed over time, and hopefully will give us samples that preserve those organic molecules that we're looking for.
How fast is the rover going? What's the typical pace between, say, RockNest and Mount Sharp?
So the rover drives about as fast as a person walks.
Okay.
So, and in a typical day, we don't drive all day. We drive for a little while, and then it stops along the way. So we drive 100 meters a day is a pretty good day.
Okay. Well, it is carrying like a spectrophotometer and like all this other stuff. You wouldn't want to be running around with that, I guess.
Right, exactly. So you want to go, not to mention a nuclear power source.
Oh, yeah.
Yeah. But, mostly it's just it's a priceless asset on the surface of another planet, and we got to be careful with it. We can't go, freewheeling around. We got to take our time and do it right.
Great. All right. Well, Lori Leshin, thanks so much for talking with me.
My pleasure.
Lori Leshin and colleagues write about volatiles, isotopes, and organic molecules at Rocknest as part of a special package of reports from Mars's Gale crater. You can read this week's articles, plus past papers from the Curiosity team, at www.sciencemag.org/extra/curiosity.